Hello, everyone. I hope you're doing well. This channel delivers videos that promote the importance of mathematical modeling techniques. In a previous video, I showed that the calculated values in the Collatz conjecture decrease by using a dynamic model based on the Collatz operation. However, when attempting a mathematical proof using that numerical model, there is a serious problem, as I will explain later. To solve this problem, starting today, I will introduce the Collatz-Rope model, which can strictly represent the changes in the values obtained by iterative calculation. As shown in the previous video, when an odd number appears, the Collatz operation uses the formula y equal 3 times x plus 1 to calculate the next step. The average rate of change of this operation becomes smaller than 1. Therefore, according to the dynamic model based on this average rate of change, the calculated values of iterative calculation, starting from any natural number, can be expected to show an overall decreasing trend. However, because this dynamic model contains approximations, we cannot conclude that the calculated values always decrease. In addition, the model cannot guarantee that the calculated values eventually reach 1. As I mentioned in a previous video about the Collatz conjecture, I am not a mathematician. I am a chemical engineer who uses mathematical methods to clarify the characteristics of reaction phenomena. Therefore, I treated the values obtained by iterative calculation in the same way as experimental data handled in chemical engineering. I carefully observed the completely different behaviors of calculated values that depend on the initial value and constructed a new mathematical model. Unlike the dynamic model introduced previously, this new model can strictly represent the changes in values produced by the calculation algorithm of the Collatz conjecture. Figure 2 shows the changes in calculated values when the initial value n sub 0 is 27. In 1,10,101,010,101, both calculated values change in completely different ways. However, careful observation reveals that the calculated values change along numerical curves expressed as odd numbers h sub k multiplied by 2 to the power of q sub k as the number of iterations increases. Here, k represents the order in which h sub k and the exponent q sub k appear. Figure 3 shows the curves of h sub k times 2 to the power of q sub k, where h sub k takes values from 1 to 19. For example, the numbers obtained by multiplying the odd number 7 by 2 to the power of q sub k are 7, 14, 28, 56, and so on. Each curve consists of an odd number at its end, followed by numbers that increase by multiplying by 2. I name these curves Collatz ropes. To distinguish each rope, when the terminal odd number is 7, I call the set of numbers the Collatz rope with odd number 7. Collatz ropes have the following characteristics. 1. The ropes exist infinitely, as many as the number of odd numbers. This is because each rope has one odd number at its end. 2. Each rope is a set consisting of the terminal odd number h sub k and infinitely many even numbers h sub k times 2 to the power of q sub k, which increase by multiplying by 2 to the power of q sub k. This is as described earlier. 3. The natural numbers that form each rope do not appear in any other rope. This is because each rope has a different odd number h sub k, and the even numbers are obtained by multiplying that odd number by 2 to the power of q sub k. This characteristic can be proven as follows. The natural numbers on a Collatz rope are given by the general formula h sub k times 2 to the power of q sub k. Now consider two Collatz ropes, y equal h sub 1 times 2 to the power of x and y equal h sub 2 times 2 to the power of x, as shown in figure 4. Assume that the values y on each rope are equal at x equal x sub 1 and x equal x sub 2. Then, equation 1 holds. We transform equation 1 as follows. The left-hand side is a division between odd numbers. If the quotient is an integer, the calculated value must be odd. On the other hand, the right-hand side is a power of 2, so must be even. This contradiction means that the assumption in equation 1 is incorrect. Therefore, it is clear that the numbers in each rope are not included in any other rope. 4. The ropes never intersect. This is because each rope begins with a unique odd number h sub k, and all subsequent even numbers increase with the same rate 2 to the power of q sub k. This can be easily inferred by looking at the shapes of the curves in Figure 1. 5. The rope with the largest number of elements is the Collatz rope with terminal odd number 1. The values of iterative calculation finally slide down this rope and become 1. This is an essential characteristic for the calculated values to reach 1. To understand the characteristics of the Collatz rope model, let us observe the changes in iterative calculation for n sub 0 equal 56, as shown in Figure 5. The initial value 56 can be expressed as 7 times 2 to the power of 3. Thus, 56 is a value on the Collatz rope with odd number 7. Dividing 56 by 2 3 times gives n sub 3. This value 7 is odd, so we calculate 3 times n sub 3 plus 1 to obtain n sub 4. This value is the even number 22, which can be expressed as 11 times 2 to the power of 1. Therefore, it lies on the Collatz rope with odd number 11. Dividing it by 2 once gives n sub 5 equal 11. Repeating the same procedure, the iterative calculation moves to the Collatz ropes with odd number 17, 13, and 5, and finally moves to the rope with odd number 1, where the calculated value becomes 1. The changes in calculated values resemble the following image. In the space of natural numbers, many ropes exist, each with an odd number at its end. A monkey walks across these ropes one by one, eventually reaching 1. Figure 6 illustrates this tightrope walking motion. If the number on the rope the monkey is holding is even, the monkey slides down the rope to the terminal odd number h sub k. Then it swings and jumps to the next rope. The value on the rope immediately after the jump is given by the calculation 3 times h sub k plus 1. Since this value is even, dividing it by 2 causes a slight descent. If the resulting number is even, the monkey continues descending the rope. If it is odd, the monkey immediately moves to the next rope. Repeating these actions, the monkey eventually moves to the rope with odd number 1 and descends to reach 1. If we can show that this sequence of actions occurs for all initial values, the Collatz conjecture is proven. However, the monkey might continue climbing a rope for some initial value and fail to reach the rope with odd number 1. In any case, by comparing the changes in calculated values to a monkey walking across ropes, the phenomenon becomes much easier to understand intuitively. To verify these changes in calculated values, I created a computer program in the C language. Normally, the effective number of digits handled in C is about 16 digits. With this number of digits, it is not possible to observe sufficiently large changes in calculated values in detail. Therefore, I designed the program so that the effective number of digits can be expanded as much as possible. The program is uploaded to GitHub, and you can download it from there. Figure 7 shows an example of iterative calculation for n sub 0 equal 27 using the computer program. If we input any natural number as the initial value, the program performs iterative calculation according to the algorithm described earlier, and the calculated value eventually becomes 1. This shows that the iterative calculation in the Collatz conjecture proceeds according to the Collatz rope model. However, it is not guaranteed that the calculated value becomes 1 for all initial values. Therefore, many researchers continue to challenge the proof of this fact. The output results include not only the calculated values, but also the types of Collatz operations, their final proportions, and the number of iterations. I use a personal computer equipped with the following processor and 16 gigabytes of RAM. With this environment, it is possible to calculate up to an effective number of 100 digits. In other words, initial values up to the order of 10 to the power of 100 can be calculated. The iterative calculated values in the Collatz conjecture proceed as tightrope, walking through Collatz ropes. This visualization has made it much easier to understand the changes in calculated values. Starting from the next video, I will explain the 5 major points that characterize tightrope walking through Collatz ropes, and I will describe the proof I constructed. That concludes today's talk. I look forward to seeing you again in the next video. Until then, take care.